talk is a talk by Kim Seongjeong on arranging parities for nodes in product of surface wise. Please.
Oh, thank you. Thank you for introduction. Yeah. Can you hear me?
Yes.
Yeah. Okay. First of all, thank you for giving me the opportunity to give a talk in this international conference. I'm very glad that I can talk about my work. In this talk, I will talk about knots in oriented surface times S1. Roughly speaking, actually, the knots in S3 times S1 is a kind of modification of virtual knots because virtual knots can be considered as a knots in thickened surface. It means orientable surface times 0, 1 interval. Then by attaching two boundaries, we can get such three manifolds and we can get knots in S3 times S1. Of course, we may apply this one to study classical knots and virtual knots, but in this talk we will focus on the knots, just knots in these three manifolds. First, let me remind how links in S3 times S1 and its diagrams are defined. Links in surface times S1 is a smooth embedding of disjoint union of circles into S3 times S1. And if it had one component, then we just call it a knot in S times S1. Through this work, we'll describe the knots and links in surface times S1 by using such a schematic description. Here, this cube means surface times 0, 1 interval, and by connecting the arcs outside of the cube, we describe that it is placed in surface times S1. And two links in surface times S1 are equivalent if one of them can be obtained from another by finite sequence of diffeomorphisms and stabilization and destabilization of S3 times S1. Here, stabilization and destabilizations are, roughly speaking, addition and deletion of handles from SG. And now let's see how we can construct the diagrams from links in S times S1. And actually, idea is very simple. We fix one point in S1, and we cut S3 times S1 at S3 times X0, and then stretch it. Then we get such a surface times 0, 1, and links becomes the union of finitely many arcs and finitely many curves. Now, since we have finitely many curves, arcs and closed curves, we can project it onto the plane. Then we get such diagram with finitely many points, which are related to boundary points of arcs. As we did in virtual knot theory, we can give over-under information or virtual crossing for intersections. And now we replace vertices, the points ABC, by double lines in the following way. For each point on the diagram, it corresponds to two boundary points on S times 0 and S times 1. Then we will replace the point by double lines so that the longer line, is connected to the arc corresponds to the arc which is connected to top side of S times 0, 1, and shorter one is connected to another one. In this manner, we can get a virtual knot diagram with double lines and it presents links in surface times 0 S1. Moreover, one can find the finitely many local moves to present equivalence relations of links in surface times S1. Here, those 7 moves are nothing but generalized Reidemeister moves. Of course, they are needed because if we see how the diagrams are constructed. And here, 3 more additional moves related to double lines. Here, especially, I want to highlight this move. Actually, here, in this move, we change over under information with additional 2 double lines. And they correspond to links in surface times S1. Locally looks like this. Here for this diagram, such link with such 2 local arcs. And for this diagram, we a link locally looks like this correspond. Here we notice that this part, the arc connecting outside of this part, means this arc, this part rotates along S1. And if we imagine that this link locally placed in surface times S1, then we can find the band which rotates along S1. And by pushing this part along the band, we can get the left part. It means even we can get a diagram on plane with classical crossings for links in S times S1. We may lose the over under information because of this move. But even we lose over under information, still we need to add such 2 double lines which present the arc rotating along S1 in S8 times S1. So our first goal is to use this information for to study knots and links in surface times S1. And firstly, let us define the degree of knots in surface times S1. For an oriented knot in K in S8 times S1 and D a diagram. For each double line, we give plus minus 1 with respect to the orientation of the knot. Then the degree of K is a summation of plus minus 1 for all double lines of D. For example, in this diagram, we have 2 double lines with plus 1s. So the summation of them is equal to 2, and the 2 is the degree of knot corresponding to this diagram. And for this one, there are 3 double lines with plus 1, so it has degree 3, and this one has degree 0. Even we define the degree of K by using the diagram and the signs for double lines. Since the double line means the part which rotates along S1. So the degree of K is nothing but the number of rotation of the closed curve presenting K in S times S1. And now a little bit modify this one to give to get more interesting information. For a crossing C of a diagram with double lines, we take a closed curve on diagram, starting from the undercrossing and ending at overcrossing of C. Then for a crossing C, we give a label valued in Z degree K by giving the summation of plus minus 1 for double lines on this closed curve. For example, in this diagram, actually the degree of K is equal to 3. And for this crossing, we can take gamma C like this. And on the gamma C, there are one double line with plus 1. So the label of C is equal to 1. Similarly, for this one, the degree of K is equal to 0. And for this crossing, we take gamma C like this. And since there are two double lines with the minus 1s on the gamma C, so we get the label minus 2. And similarly, this label has such geometric meaning. The label of crossing C means how many times the closed curve from undercrossing to overcrossing turns around S1. And actually, these labels satisfy the following properties, which looks similar to the parity axioms for in virtual knot theory. For the crossing, which can be removed by radius move 1, it has label 0. And for two crossings on the bygone have same degree. And for three crossings in radius move 3, they satisfy such equality. And for two crossings in the crossing change move, the labels satisfy such equality. Moreover, in the label, if we consider the labels for classical crossings modulo 2, then it becomes the parity, which is frequently used in virtual knot theory. And if we separate it, then the labels by label 0 and others, then it becomes a weak parity. And now let me introduce more interesting example. Sorry. Now let's extend this concept in more to the general case by using actions. For an abelian group A, a winding parity of a degree on a diagram for each crossing is, roughly speaking, the way how to give the value elements in A satisfy those conditions. Actually, the conditions for winding parities are coming from the properties of labels of crossings, which is defined in the previous section. But one difference is here for the crossing change move, there are winding parities for those two crossings that satisfy such equality. Then, of course, the label, which is defined in the previous section, is actually winding parity. And the Gaussian parity is also a winding parity with an abelian group Z2 and the fixed element is equal to 0. And let me introduce one interesting example of winding parity, by which is defined by using the homology, first homology of ambient space S times S1. Here, for crossing C, we consider the pre-image of the crossing in times 0, 1, which is appeared when we define the diagrams. Then we get two arcs with points which correspond to the crossings. And here we connect those 2 points by vertical line VC, and we take closed curve starting from this point and which ends at this point. Then we can get a closed curve in S times S1. And we can consider it as a closed curve in S8 times S1. And now for the crossing, we give the equivalence class of this closed curve in a first homology of S8 times S1 quotiented by K, where K is the equivalent class of K in in first homology of SG times S1. And we call this homological winding parity. Then we can show that this is actually this homological winding parity is actually winding parity with abelian group H1 SG times S1 quotiented by K with the fixed element A. Here, one interesting part is by Kenneth theorem. We can get such a relation between this abelian group and the direct sum of 2 abelian groups coming from surface, underlying surface, first homology of underlying surface and first homology of S1. And actually we have a projection map to this direct sum. And if we consider just this part, then we can get the label, which is defined in previous section. And moreover, if we consider just this part, then it becomes an orientable parity, which is one of generalization of parity considered by Igor Mikhailovich. And here, one interesting point is here the fixed element is star times S1. And why this is the fixed element is star times S1? Because actually the double line was presents such kind of situation in S8 times S1. But in some sense, if we change, if we define another winding parity by using first homology with different element, then we may give different meaning for double lines, even if it is the diagram with double lines comes from the links in S times S1 with rotation along S1 once. So our last question for this topic was that this one. Is there exists a universal object for winding parity? Here, universal winding parity means the winding parity P UW and valued in A UW, such that for any winding parity, there exists a group homomorphism, so, which make this diagram commute. And of course, there exists because where abstractly we can define a UW and winding parity by taking every crossing as a generators and every double lines as a generators, and we quotient out by relations coming from the properties of winding parity. But then the question is there a geometric model for winding parity? And actually, yes. First, we take a diagram, and then we put points on double line on crossings, and we put points on the double lines and attach circles on the points related to double lines, and then we connect 2 points corresponding to classical crossings, and then we attach disks where such a angle was in plane minus diagram. For example, here we have a bigone. Then we attach disk here along the arcs corresponding to the edges of these bigones. By making a complex in this manner, we can get a complex CK. And actually, for CK, the first homology of CK generated by closed curves, which starting from undercrossing to overcrossing for each classical crossings, and SIs, which are corresponding to circles attached in double lines. And they satisfy the actions for winding parities. And moreover, finally, we can prove that this one. Oh, sorry. I'm so sorry. Here, if we take every first homology, run over all possible diagrams of K, then it is isomorphic to the universal winding parity, which was defined abstractly. It means this one is a universal winding parity. So our next question is this one. Actually, when we now define the universal winding parity by using complex, we attach it closed curves. But when we show that as the show that it is isomorphic to the winding parity, actually here I skipped this part, but we make all generators corresponding to the closed curves are same. But if we consider surface times S1, where the boundary of surface is non-empty, then by distinguish them, we may present that even this part rotates around S1, we may distinguish which boundary along which boundary it rotates. And actually this is important because in a classical link in S3, if J fibered knot, then K can be considered as a knot in complement of J. And actually, since J is a fibered knot, so this is isomorphic to sigma J times S1, where sigma j is a Jarvis surface of J. So by using this part, we can expect that our winding parity and our modification of winding parity can be used to study classical rings. And that's all of my talk. Thank you very much for
Thank
attention.
you. Any comment? Question?
Yes, I have a question. По-русски, да, можно? Или лучше по-английски? My question,
по-русски можно.
вы напомните, вы эти узлы в S1 на SG рассматриваете, они могут произвольные классы гомологий? Или это нулевые классы? Я прослушал начало. Вот эти сами узлы, какие гомологии поверхности SG на S1? Сами узлы, да, могут
может,
они вдоль S1
может не тривиальные.
Тривиальные? Любые. А вот такой вопрос.
Не тривиальные.
Нетривиальные. А вот ваш winding number, twisted winding number, который вы определили, может помочь решить такую задачу. Вот если узел строго вертикальный, из точки растет вдоль S1, то он пересекает SG в одной точке. А если у вас узел крутится за счет вашего препятствия, которое вы там универсальное делаете, то минимальный род секущей поверхности, скорее всего, увеличится. Вы можете прокомментировать, верно это или нет, что, оценивая ваш вариант, можно как-то снизу оценить, это не поверхность Зейферта, но близкое понятие, поверхность, которая пересекает узел в одной точке и имеет минимальный род среди всех. Ну а если это нулевой узел, то это значит поверхность, которая не пересекает узел, а когда winding number набегает, то такой поверхности без увеличения рода не бывает, скорее всего. Или вы не знаете эту задачу?
Прошу прощения. Спасибо за интересный вопрос, но прошу прощения. Я не могу ответить. Я имею в виду, я не думал об этом, и сейчас я не могу ответить на ваш вопрос. Прошу прощения.
Интересный вопрос. Спасибо за ответ.
Спасибо.
Нет? Тогда еще раз благодарим докладчика.